Alrighty, folks, and now we're moving into our final lesson for Unit 1, Lesson 5 of 5 for Unit 1. So in this lesson, we're going to talk about horizontally stretching and reflecting functions, and we're also going to put them all together. All of the transformations we've discussed, we're going to look at situations where we might be doing any combination of a translation and a stretch and a reflection. So we'll get into that in a moment here. As always, though, here are kind of the big ideas, the key takeaways for the lesson. You can kind of use this as a little checklist. After you've watched, you can come back, pause the video, and go through and say, okay, what do I feel pretty good about? What do I maybe need a little more practice with? Okay, well, let's jump in. So as I said, we'll just do a little, recap of where we've been before we start thinking about where we're going with this today. Okay, we've been talking about transformations, right? Taking the graph or the equation or both for a function and thinking about different ways we can alter it, right? And we've looked at translations. Remember, that's essentially sliding or shifting the graph around either up or down or left or right or both. So a constant, and when we did that, we were taking a constant, which we called h for horizontal or k for vertical, was added or subtracted to each x or y value, right? If you add something to each x value, you're shifting it to the right. If you subtract something from each x value, you're shifting it to the left. If you add something to each y value, you're shifting it up. If you subtract something from each y value, you're shifting it down. And this results, like we said, in the graph kind of sliding around, a translation. Then we looked at vertical stretches. So this wasn't just like sliding the graph up or down, it was actually stretching the graph, changing its shape, right? Maybe making it go, up or down faster or less fast, depending on how big that vertical stretch was. We use the parameter a to represent a vertical stretch. It's a constant a. And since we're actually stretching, changing the shape of it, we're not just adding or subtracting something to each y value, we're actually multiplying each y value by that constant, a, the vertical stretch parameter. And that resulted in the graph, again, being stretched upwards or downwards, okay? Or, both, really. It's stretched vertically about the x-axis, we say. And then very closely related to those vertical stretches were vertical reflections across the x-axis, right? And those occurred, remember, when that constant, a, that we were multiplying each y value by, was negative. For most of the ones we looked at in the previous lesson, a was just -1, but that's because we were mostly focusing on, at that time we were still just doing a reflection and not a reflection and a stretch. We'll start to see today cases where we do both a stretch and a reflection. Okay, so most of the ones we've looked at, a, if it was negative, was just going to be -1, so that we didn't have both a stretch and a reflection occurring. But we'll start to see things where a might be -3 or -4. And that's still a reflection. It just means not only was it reflected, it also then got vertically stretched. Okay? This caused the sign of each y value to change and therefore swap to the other side of the x-axis, right? As we talked about, if we're multiplying each y value by a negative number, well, if the y value was positive before and above the y-axis, now it's going to be negative and below the y-axis, right? A positive times a negative is a negative. And vice versa. If the y value was negative originally, meaning it was below the x-axis, multiplying a negative by a negative is going to give us a positive. So now the new y value will be above the y-axis, right? And that's why it causes it to swap sides over the x-axis, right? To get reflected across the x-axis. So in this lesson, we're going to now just take that one step further. You can probably tell the pattern here. We did vertical and horizontal translations, and then we only did vertical stretches and vertical reflections. Well, today, let's add in horizontal stretches and horizontal reflections, because we can also do that. We could stretch the graph sideways, okay? You can probably guess if vertical stretches involved multiplying every y value by a constant, a, then horizontal stretches are going to involve multiplying every x value by some constant. And then, as I said, we'll look at combining all of the transformations we've studied so that we're doing, potentially many things to the equation or the graph of a function. All right, so jumping into horizontal stretches here, okay? Again, vertical stretches, we multiplied the outputs, the y values, by some constant, a. For a horizontal stretch, since x is horizontal, this happens when we take the input, the x's for a function, and we multiply those by a non-zero constant. B, we're going to give it, right? So A for vertical stretches, B tells us about the horizontal stretch. So the result of doing that, if we multiply each x value, if in the function we replace each x value with bx, okay, what we get is a horizontal stretch of the graph about the y-axis. Again, all that terminology means, it is important terminology, but all it means for about the y-axis is that we're kind of anchoring it at the y-axis. We sometimes say like we're stretching away or towards the y-axis, right? If I was to stretch this horizontally, you can think of it almost like it's pinned here, and I'm gonna pull it this way and pull it this way. I'm doing it everywhere, but it's kind of all happening about the y-axis here. And the reason it's important to specify that is because it is technically possible to stretch it about any line horizontally, right? We could take that same graph and we could stretch it about, instead of the line x equals 0, the y-axis, we could stretch it about the line y equals 2. And then that's kind of our anchor point, and we stretch it horizontally away from that, right? Or again, we could do towards that line, compress it kind of, okay? Now again, we're not gonna deal with stretches like that in Math 30. We are only ever gonna stretch vertically about the x-axis or horizontally about the y-axis, but it is still, you know, an important part. When you're describing the transformation that happened, you should mention that it was about the y-axis. That will always be the case for a horizontal stretch in Math 30, but still an important thing to clarify. What are you stretching it about? Okay. Now, key point here, key point. If we have this parameter b, okay, this constant b, the result is a horizontal stretch of the graph about the y-axis, yes, but it's not actually by a factor of b, it's by a factor of 1 over b. Every x doesn't actually get multiplied by b, it gets multiplied by 1 over b. Or another way you could think of that is it gets divided by b. And again, the absolute value of b, okay? Reminder, absolute value just means the size of the number without giving meaning to whether it's positive or negative, okay? That's how much it's going to be stretched by. So like, for example, if our b is -2, we would say it's a horizontal stretch by a factor of positive 1 over 2, okay? If b is negative, again, since this involves that multiplication, it's going to change the sign. If b is negative, it's also going to cause a reflection across the y-axis. We'll talk more about that later when we get into the horizontal reflection part of this lesson, okay? But here's what's happening in a horizontal stretch, okay? This is it. Every single x value on the original graph is getting multiplied by 1 over b, okay? Now, why 1 over b? Why with a vertical stretch were we just multiplying by a, but now with a horizontal stretch, we actually end up multiplying by 1 over b? Again, it's the same thing we talked about with those horizontal translations. It makes sense when we remember that x is not isolated in our function's equation. Okay, so again, I know it's a little counterintuitive at first that multiplying our inputs by b causes a horizontal stretch by a factor of 1 over b, but it does make sense after some thought. Remember, in the function y equals f of x, the isolated variable is always y, not x, right? We always have y equals stuff if we've written it in our usual notation, right? And if it's not written in that notation, we should get it into that notation, okay? It's never x equals stuff. It's always y equals stuff. So what we're doing here, right, what we're doing when we do a horizontal stretch is effectively replacing x with some new bx, right? Bx. And what we want to do is consider the resulting effect on the horizontal stretch of the graph, right? What actually happened to every x value if we replaced x with bx? So in order to do that, to think about how each x value is affected, since that's our horizontal axis, let's just think about, you know, rearranging the equation so that x is actually isolated, because that will let us see what did we actually do to the x values when we replaced x with, in this example, 2x. So let's just start out with a simple example. Let's just say we had, you know, y equals x, okay? And we wanted to stretch the graph horizontally by replacing our x with 2x. In other words, we wanted to make our b be 2, right? We wanted to make b equal 2. Well, what would our equation become then? Instead of y equals x, if we're replacing x with 2x, making b equal 2, we would now have, instead of y equals x, y equals 2x, right? And now if we want to think about, okay, what was the actual horizontal stretch? What actually happened to every x value, right, when we did that? If we want to see the effect that that change had on the x values, an easy way to do that is to solve this equation for x, right? Because we know before, x was just equal to y. So if we can figure out what is x actually equal to now, that'll show us how the x values have changed, okay? So in order to investigate that, here we go. Look, we replaced x with 2x, right? In order to solve for x and see what happened, what are we going to do? We're going to divide both sides by 2. Now, again, we don't actually have to do this when we're examining horizontal stretches. For the most part, we can just get comfortable with, okay, b is 2, so that means a horizontal stretch is a factor of 1 over 2. But to get the logic here, to see why it makes sense that we multiply every x value by 1 over b, okay, let's actually go ahead and do that. Let's isolate our x, okay? And look at this. X now equals, by replacing x with 2x, we can now see that if we were to figure out, well, what happened to our x's then? They're now not equal to y like they were before. They're equal to y over 2, 1/2 of y, right? Originally, the x values were just equal to the y values. It was y equals x. But by replacing x with 2x and seeing, okay, what does that do to the value of x? We can now see that they're actually half as large, right? Not twice as big, half as big. Now x is equal to not y, but y over 2, right? So on this graph where x was 1 and y was 1, well, on this transformed graph, now when y is 1, x is just going to be 1/2, or 0.5, right? A point on this graph would have been 4, 4. When x was 4, y would be 4, right? On this graph now, when x is 4, or sorry, when y is 4, x is only going to be 2. It's half as big. It used to be, you know, when x was 4, y was 4. Now, when y is 4, x is only 2. The x has gotten half as big, right? So in other words, when our b equals 2, we can see from the equation that every single x value actually ends up getting multiplied not by 2, but by 1 over 2, okay? It's because of that, you know, inverse opposite operation effect. Since x isn't isolated, whatever we're kind of doing to it here, if we want to consider what effect that actually had on x, we're going to end up doing the opposite operation in order to isolate x and figure out what the effect was, right? We've seen this idea before, where the opposite operation is ultimately applied to the x value. We saw it in the previous lesson and in Math 20 when we studied horizontal translations with the parameter h, right? So again, just another example to remind ourselves of how this isn't as weird as it seems at first, right? Because if we had, you know, if we wanted to make a transformation to a function f of x by making our h value be 3, f of x minus h, so we can see that our h is positive 3, right? But again, it's a little weird for students sometimes at first that why is it minus 3 if it's moving to the right, right? So doesn't that make the 3 feel negative? Right? And again, we can say, well, it's supposed to be x minus h, but that might not be the most satisfying answer in the world because that just begs the question, why is it x minus h? Why not x plus h, right? But it's because of this inverse operational effect, right? Because that would translate f of x 3 units right. We know that y equals f of x plus 3 would translate it 3 units left. And it's because, again, x isn't isolated. If we wanted to isolate x, we would ultimately perform the opposite operation to each x value when considering their movement on the graph. So as a result, that y equals f of x minus 3, where it kind of looks like we're subtracting 3 from x. If I actually wanted to solve for x, though, I'd be adding 3 to both sides, meaning that x will be equal to something that is, you know, plus 3 compared to what it used to be. And same thing here, minus 3 compared to what it used to be, right? This actually adds 3 to each x value if we were to isolate x. and this actually subtracts 3 from whatever it used to be equal to, right? Just another simple example here. If y equals x were to become y equals x minus 3, and we asked ourselves, okay, how has each x value changed? Well, x used to just be equal to y, but now x is equal to, if I add 3 to both sides, x is actually now equal to y plus 3. So every x value has been moved, higher by 3. I shouldn't say higher, to the right by 3, right? If x used to be at 0, now it's at 3. That's moved it 3 to the right. If it used to be at, -1, now it's at +2. That's moving it 3 to the right. So for anything horizontal, anything happening to x, there's always kind of this opposite operation thing happening, this inverse operation thing happening, where, what kind of looks like it might be happening to it on one side of the equation, if we were to isolate x and actually study the effect of that transformation, we realize that, we do the opposite operation to isolate x. So there's kind of this opposite thing going on with x, right? And again, it makes sense. It's not just a weird rule to remember. It's just because x isn't isolated. So if we get back to b and our horizontal stretches, we just took a little detour there to remind ourselves of the translations, okay? We're going to look at some different examples here. And in these examples, to keep things simple, okay, I'm just going to label one point as the graph is stretched horizontally, the point that was originally at x being 2, y being 4, on a graph that we know and love, y equals x squared. But you can look for yourself and you can see that every single x value in each of the following examples is really just being multiplied by whatever b is, it's being multiplied by 1 over that, right? By 1 over b. Okay, so in all of these horizontal stretches, every single point just gets multiplied by not b, 1 over b. And I should be more specific there, sorry. Every single x coordinate for a horizontal stretch is just getting multiplied by 1 over b. So take a look at these different, equations and the resulting graphs, right? Y equals x squared, kind of like our base parabola, the one we can kind of compare other ones to figure out what's happened to it, right? Y equals x squared. Well, b is just 1 here, right? You could think of this as 1x being squared. And so it has the point 2, 4. Again, makes sense because 4y equals 2x squared, right? 4 is equal to 2 squared. Y equals x squared. So that's why that point is on our graph, right? 1, 1 is on our graph because 1 equals 1 squared. -2, 4 is on our graph because 4 equals -2 squared, okay? Now, if we replace x with 2x, notice the difference here, okay? A common student mistake is to say that this is also a horizontal stretch by a factor of 2. But have we actually taken our original equation and replaced it with 2x here? No, we've actually just multiplied our original equation, all of it, by 2. This would actually be a vertical stretch by a factor of 2, right? This part was my original equation, and I've just multiplied the whole thing by 2. This is actually just multiplying each y value by 2, okay? So always be careful with that. Have you actually replaced x with some bx? And that is what we're doing here, right? It used to be y equals x squared. Now it's y equals 2x squared, right? So we can see that our b is 2, which means what are we going to multiply every x value by? We're going to multiply every x value by 1 over b. So 1 over 2. So every single x on this graph has now, when we go to this one, we should see that it's changed by a factor of 1/2. Sure enough, take a look. X used to be 2 when y was 4. Now x is 1 when y is 4, right? 2 times 1/2 is 4. Or sorry, no, that's not true. 2 times 1/2 is 1, right? Half of 2 is 1, okay? The y values aren't affected by this horizontal stretch, okay? The x values are all multiplied by 1/2. And you can, like I said, you can check for yourself. I'm only showing one point to keep things from getting too crowded. But look here, the point that was at 1, 1, we can now kind of see it's at 1/2 1, or 0.51, right? The point that was at -2, 4 is now at is now at -1, 4, right? We've multiplied that x value by 1/2 as well. Okay, moving along here, b equals 3. Notice, again, I've replaced x with a bx, right? X has become 3x in the equation. So, pop quiz, what does that mean we're going to multiply each x value by? Well, not 3, right? 1/3, 1/3. Sure enough, look at this. Compared to y equals x squared, the graph of y equals 3x being squared gives us this, right? 2 times 1/3 is 2/3, which as a decimal is 0.6667. The software I use to make these graphs wouldn't show me fractions. I wish it would have. Okay, so, right? Pretty cool. Okay, and then we've got here, our b is 1/2. We've replaced x with 1/2 x in our original function. Okay, so if we take a look there, what would that mean? Remember, we're going to multiply by 1/b. So what is 1/1/2, right? I mean, we can think of that as, well, 1 over anything is just its reciprocal. So 1/1/2 should just be 2/1 or 2. But you can also rely on the fact that, you know, if we've got 1/1/2, that's our horizontal stretch, right? You could also rely on the fact that dividing by a fraction is the same as multiplying by its reciprocal. So dividing by 1/2 is the same as multiplying by 2/1, right? Which just gives us 1 times 2, which is 2, divided by 1, which is 2. So in this case, every single x value is being multiplied by 2, because that's 1/b, right? If b is 1/2, then 1/1/2 is just 2. We're multiplying every x value by 2, and sure enough, look what happened to that point, right? It has now ended up not at 2, 4, but 4, 4. So when b is greater than 1, right, we end up making it skinnier. It is a horizontal stretch, but it's a horizontal stretch by a factor of 1/2 and 1/3 for these ones, right? So we still call it a stretch even though it's getting narrower. We always call it a stretch, otherwise it gets confusing. Like if I were to say a horizontal compression by a factor of 1/2, again, would that mean that it's been, you know, it's now 1/2 as wide, or does it mean it's 1/2 as compressed, meaning that it's actually more compressed, meaning that it's actually, 1/2 as compressed, meaning that it's actually less compressed, meaning that it got wider. Do you see what I mean? If we use those terms compression or shrink, it can just get a little bit confusing. If we always call it a stretch and we just let the number tell us whether that means it got wider or narrower, we won't run into that problem of confusion. Okay, so we'll stick to the terminology stretch, even if that stretch resulted in it, you know, kind of looking less stretched. We'll let the number tell us that. A horizontal stretch by a factor of 1/3. Okay, so it's 1/3 as stretched. It's kind of been compressed. Okay, so there we go, right? And again, you can look at any point on here and you will see that. The point that used to be at 1, 1, look where it is now. On this graph, it's at 2, 1. Each x value has just been multiplied by, in this case, 2. In all cases, each x value got multiplied by 1/the b value. So the notation we use for horizontal stretches, again, it's going to look pretty familiar to what you're used to, okay? That's why we use this function notation, because it's consistent. It lets us see individually what we're dealing with in terms of the transformations occurring to a function, okay? So for horizontal stretches, it has to do, like we talked about, with that b value, right? So we would write it if just a horizontal stretch was happening, that's how we would communicate it. The b does the horizontal stretching. So the mapping notation, again, remember, mapping notation is just a little bit more specific, right? A little bit more direct instructions for how to go from one point to another point. This is more general for transforming like the whole equation, right? This shows you for each x, what's happening to it? Well, it's being multiplied, like we talked about, by 1/bx, right? Y should be unaffected if all that happened was a horizontal stretch. Okay, so we've now built to the point, and we'll talk about this later in the lesson, but we've now seen all of these, right? We've seen the vertical stretch, A. We've seen the F, well, F is just the name of the function. We've now added in our B, that's the the thing we'll see that causes the horizontal stretch. We've got it gets multiplied by the x in the notation here, and then we've got our h, our horizontal translation. Okay, so you can see all the horizontal stuff kind of goes inside here with the x's, with the inputs before they even go through the function. And then all the y stuff happens to the entire equation itself. It makes sense because that's what y is equal to, right? Y is equal to the equation. So to transform y, we kind of need to do operations to the whole equation. For the x stuff, that's the inputs. So we've got to affect them before they're even input, essentially. Okay, we'll get there. We're just going to focus on horizontal stretches for now, but I just wanted to give you a heads up that we've now seen all of them, right? A, B, H, and K. Whoops, I wrote H there. That should be a K, of course. K. Okay. So just for an example, just to see what it looks like in function notation and mapping notation, if a graph y equals f of x is transformed with a horizontal stretch by a factor of 1/3, well, that means our b is 3, right? And each x value is multiplied by 1/3. Okay, 1/3, we multiply by 1 over b. So we could write this transformation as, in function notation, y equals f of 3x. Notice what we're doing there. We're replacing x with 3x, right? We replace x with bx for function notation. In our mapping notation, that just shows us exactly what we're actually going to do to every point. So since a horizontal stretch by a factor of 1/3 means that we multiply every x by 1/3, these are just direct instructions on what to do to each individual point. So if you had a point that was at xy, it's now at 1/3 x, y. Right? 1/3 times x, y. Okay, let's try this out. So some examples here. Let's stretch a graph horizontally. So we've got the equation for the graph of y equals f of x being transformed into y equals f of 2x. Okay, so function notation allows us to pick out what's happening, right? So this shows me my b is 2, but be careful. What does that mean the horizontal stretch is, right? If b is 2, then the horizontal stretch about the y-axis, right? Horizontal stretch about y-axis by a factor of not 2, 1/2. Right? So literally all that means is we multiply each x value by 1/2, or by 0.5 if you prefer. Okay? So take a look here. We're going to take this graph and we're going to multiply each x value that sits on the graph by 1/2. Okay? So they even nicely gave us a table of values here. Right? So all we're going to do, we're going to multiply these x's, because it's a horizontal stretch, by 1/2, right? So -6 times 1/2, the new point is going to be at -3 for the x coordinate, and it's not vertically stretching it or translating or doing anything to change the y values, so a new point on our graph will be -3, 4, right? So let's see. X is -3, y is going to be 4. So that point will be on our graph. -3, 4. Okay, and notice something here too, folks, right? Look, a horizontal stretch about the y-axis by a factor of 1/2. Essentially, that means each x value is going to be half as far away from the y-axis now, right? We've multiplied this by 1/2, and sure enough, that point is halfway to the x-axis from where it started, because we've multiplied the x-coordinate by 1/2. All right, continuing on here. X-coordinate of -2, if we multiply that by 1/2, that point will now have an x-coordinate of -1. Y-coordinate will still be 0, so -1, 0 will be the new y-coordinate of that point. So there it is, transformed. Okay, 0, 2, hey, what's 0 times 1/2? Well, 0 times anything is still 0. So do you have any ideas about what we might call this point? It's invariant, right? Again, what points are invariant depends on what kind of transformation you're doing. So since in a horizontal stretch we multiply the x values by 1/b, right? It makes sense that the invariant points, the ones that don't move, so in this case 0, 2, right? The ones that don't move are the numbers that aren't going to change when we multiply them by 1 over b. The only number that's not going to change if you multiply it by something is 0. No matter what b is, if I multiply 0 by 1 over b, it's still 0. Okay? Similarly to how we saw the x-intercepts be invariant to vertical stretches, because for vertical stretches, we multiply the y value by a, and for an x-intercept, the y value is 0, right? Okay, moving on here. 2, 0, where's that going to end up? Well, 2 times 1/2 is 1, and it will still be at a y of 0. Okay, and again, we can even just use points directly from the graph. The table of values is nice, but I just want to emphasize, you can also look at the graph and get your x-coordinates and see it there, right? This one has an x-coordinate of 2, so if I multiply that by 1/2, it's now going to be at 1. 2 times 1/2 is 1, right? Or up here, 6, x-coordinate of 6. 6 times 1/2 is 3, so we should see that here now, right? 3, 4. Okay, and we could do it even if we look outside of the points we were given on the table of values. For example here, right, x-coordinate of 4, the point 4, 2 is going to end up at, well, 1/2 times 4 is 2. So its new x-coordinate will be 2. It'll be at 2, 2. 4, 2 ends up at 2, 2, right? And we've got a pretty good idea of the shape of this graph now. Again, I should really use a ruler. It just doesn't work very well on the iPad, but you should use a ruler on paper, just to make it look nice and straight, okay? But there we go. That would be, if the blue one is y equals f of x, then the black one we just drew is f of 2x. That's what happens if we replace our inputs, our x's, with 2x's, right? A horizontal stretch by a factor of 1/2. And you can kind of tell that this, this looks right. That's a nice way we can check our work. Does it look like we've taken this graph and horizontally stretched it in such a way that it's now, half as wide? I would say it does, right? We took our wide W and now it's a narrower W. And it's narrower by a factor of about 1/2. Each x value is now halfway between where it used to be compared to the y-axis, right? Halfway, halfway, halfway. So this does look like we've successfully horizontally stretched it by a factor of 1/2 with a b value of 2. All right, so let's try another one here where they've given us, kind of reverse, they've given us the transformed graph. They want us to figure out what kind of stretch must have been applied to it, okay? So describe the stretch that must be applied to the graph of y equals f of x. So that's our blue one. They're saying if that's the original, what did we have to do to it to obtain the graph of y equals g of x, the red one? So that's been stretched. Well, let's take a look. Let's compare some points, right? We can see kind of there's been a horizontal stretch here. Notice how we had like a wide W-shaped graph, and now it's a narrower W-shaped graph. So that implies some kind of horizontal stretch. Let's see. How about we compare this point here? Looks like 6, 4 became, what's the corresponding point? And always be careful. Remember to find a corresponding point, right? We want to find a point that actually like matches up here. We don't want to compare this to that, for example. That's a different point, right? That doesn't correspond with this one. So this one looks like it's ended up here, right? Now it's at 2, 4. So it became 2, 4. And that's, that's technically enough to figure out what our horizontal stretch would be. Never hurts, though, to, find one more point to compare just to be double sure, right? For example, look at this point, 3, 0. Can we see the corresponding point? Looks like that has become, on the stretched graph, it looks like it's now at 1, 0, right? So 3, 0. Has an image point at 1, 0. So same thing's happening here. Look what we're doing to our x's, right? What's happening to our x's? They are all being multiplied by the same thing. No matter where we look, -6 for the x-coordinate, -2 for the x-coordinate, -3 for the x-coordinate, -1 for the x-coordinate, right? Even this one, 0 for the x-coordinate, stayed at 0. So it seems like every x value is being multiplied by the same thing, right? Each x value is being multiplied by, well, what is it being multiplied? To go from 6 to 2, we multiply by 1/3, right? Or divide by 3, you could say, right? 3 to 1, same thing, multiply by 1/3, or divide by 3 is being multiplied by 1/3, right? So we have a horizontal stretch by a factor of 1/3 about y-axis. Okay, what does that mean B is? So this is, I guess this is our answer, because they asked us what stretch must be applied, right? But we could take it, just to think a little bit, because it can be a little bit tricky. If the horizontal stretch is 1/3, what was B? What was B? B was 3, right? The parameter B that tells us about the horizontal stretch must be 3. Okay. Alrighty, so another one here with a horizontal stretch occurring, but now it's talking about the domain. We don't actually have the graph, getting us to think about what would a horizontal stretch do to something's domain. If we know its starting domain, what would the domain be now? Okay, so it has the domain, all values of x such that 2 is less than x is less than 6. So x can only be values that are between 2 and 6, not including 2 and 6, because it's strictly less than, not less than or equal to. The function undergoes the transformation. Ooh, okay, they're showing it in mapping notation. Okay, so be careful. This is mapping notation. So we went from x, y to 5x, y. What is the domain of the transformed function? Now remember, this mapping notation's a little more direct. It's exact instructions on how to go from your original point to your new point, right? In function notation, it's talking generally about how to transform the equation. Mapping notation, it's just saying the x's are going to become 5x. So what does that mean? Each x gets multiplied by 5, right? It's a description. If x used to be, 2, now it's at 10, 5 times 2. If x used to be at 4, now it's at 20, 5 times 4. Okay, so each x gets multiplied by 5. So what's that going to mean for our domain, right? Well, our original domain was from 2 to 6, right? If we want to visualize that on a number line, let's say, it went from 2 to 6, right? That was our original domain. Open circles because 2 and 6 were not included. Okay, what happens to that domain if we multiply every single x value on our graph or in our function by 5? Well, 2 is going to get multiplied by 5 to become 10. So our old minimum x value was 5. That's now at 10, right? And our old maximum x value for the domain was 6. Well, that's going to get multiplied by 5 as well to become 6 times 5 is 30, right? So this is our new domain. Used to be from 2 to 6, now it's from 10 to 30. Mapping notation here shows us every single x value in this graph is just getting multiplied by 5. So our new domain will be the set of all x's such that 10 is less than x, which is less than 30. And x is an element of the real numbers. And there we go. That's the new domain. B here, our B value, right? Just for getting the hang of that, because it can be tricky at first. If each x got multiplied by 5, right, we had a horizontal stretch by factor of 5. What is B? B would be 1 over 5, right? 1/5. So careful there. Again, the mapping notation is showing us directly what's happening to each x coordinate. Okay. Let's just take a look at this. All right, so now that we've talked about it a little bit, right, we can see, just to visualize, right, the effect of B. Notice I've graphed two things here, y equals x squared in blue, and y equals replacing x with bx, and then I can mess around with the value of b here. We can see how that affects the graph, right? So notice when b is 6, that's where I've got it set to now, each x coordinate has been multiplied by 1 over 6, right? So the x coordinates have gotten 1/6 as large compared to their original points. The image points have 1/6 the x coordinate. When I make b, for example, let's say 0.5, right, you can see it looks wider, and each x coordinate has been multiplied by 2 in that case. It's kind of hard to get it to stay. There we go, right? Each x coordinate has been multiplied by 1 over 0.5, which is 2, right? That point that used to be there at an x coordinate of 1 is now here at an x coordinate of 2, right? So we see that happening here. Okay. So this works for, of course, any, function. If I did y equals x versus y equals bx, right? It's the same thing. It's a horizontal stretch. So we can see when I make it larger, the x coordinate of the corresponding points is getting smaller. When I make it a number that's smaller than 1, like 1 over 0.5, now I'm multiplying those x coordinates by 2 if b is 0.5. And so the x coordinates get more spread out. They're stretched horizontally about the y-axis outward from the y-axis, okay? And so that's what we're dealing with there. Let's head back to the notes here, and you can go ahead and give this one a try, just getting your bearings with recognizing that b and what that stretch actually means, okay? Again, trickiest part here is remembering that b is 1 over the horizontal stretch, and vice versa. The horizontal stretch is 1 over b. So pause the video, take a little time to practice, try some out, and then when we come back, we'll talk about horizontal reflections. A horizontal reflection, or a reflection across the y-axis, right? If we mirror something across the y-axis, we're flipping it that way. So, we had a parabola over here, and I reflected it across the y-axis, it's going to end up looking something like that, right? A reflection across the y-axis. Now, these are also caused, no need to learn a new parameter, much like with vertical stretches and reflections, both were caused by a. For horizontal reflections and stretches, they're both caused by the value of b, and that makes sense when we think about it. For the same reason a causing a vertical reflection made sense. Because remember, every y value got multiplied by a for a vertical stretch. We now know for a horizontal stretch, every x value gets multiplied by 1 over b. So what happens if that b is negative, and therefore 1 over b is also negative? Right? Well, that's going to change the sign of every x value. So in a horizontal reflection, okay, each point on the original graph is mirrored across the y-axis, and this makes sense because, again, if we consider all of these pieces of information, all x values to the right of the y-axis are positive, right? All these are positive x's, whereas all values to the left of the y-axis are negative. So these are our negative x's, these are our positive x's, okay? And since each x value is being multiplied by 1 over b in a horizontal stretch or a horizontal reflection, okay, well, if we multiply a positive number, a positive x, by a negative number, a negative 1 over b, that positive x is going to become a negative, right? Positive times negative is negative. So the positive x has become a negative x. It's changed sides. It's flipped across the y-axis. And vice versa, if we multiply a negative x by a negative 1 over b, we're going to get a positive result, right? Negative times negative is positive. So if x was negative and we multiply it by a negative number, 1 over b, it becomes a positive x. It goes from being on this side of the y-axis to this side, okay? So when a positive x value on the right of the y-axis is multiplied by a negative 1 over b, it becomes negative. It's on the left. And when a negative, one that starts out on the left of the y-axis, is multiplied by a negative, well, negative times negative is a positive. So now that new corresponding image point will have a positive x coordinate. It'll be on the right side of the y-axis. In other words, right, multiplying any x value by a negative 1 over b will always cause the x value sign to change, resulting in it swapping from one side of the y-axis to the other. So here's just an example, right? Now notice where our b is. This isn't negative f of x, this is f of negative x. We're altering the inputs, right? You can think of it as we're changing the inputs that actually go into the function in the first place, not multiplying the whole function's equation by -1, making the inputs negative, right? So our b here we can see is -1. So what does that mean every x value should get multiplied by? -1, right? And we can see that's all that's happening here. For example, this point is at, what's that, 3, -1? And if we look over here at this parabola's vertex, the reflected parabola or the transformed parabola, it's now at -3, -1. So what happened to the x? It got multiplied by -1, right? +3 became -3. And what's the result? It gets mirrored across the y-axis, right? Notice that, again, they're equidistant from the y-axis. The y-axis is acting kind of like our mirror here for the reflection, right? We could do this with any points, any points. Every x coordinate on this black one has just been multiplied by -1 to get the corresponding image point on the reflected graph, the red one, right? We can see there that 2, 0 became -2, 0. Look at this invariant point. Is that where you would expect to have an invariant point, right? It was at 0, 8. Now it's at still 0, 8. Well, yeah, that makes sense because 0 times -1 is still 0. So this actually won't have changed its location, right? Every other point, you notice over here, -6, 8 is now at, or sorry, I had that backwards. +6, 8 is now at -6, 8, right? It's been reflected across. Every point just has a mirror image of itself across the y-axis, a horizontal reflection across the y-axis, having been caused by multiplying every x by a -1 over b. So it's the exact same notation. Again, you don't have to learn any new parameter or anything. It's still just b that's causing this reflection because b gets multiplied by every x. Well, 1 over b does, okay? So it's the exact same as for horizontal stretches because both are caused by b. It's the size of b, right, the number that determines the amount of stretching, right? And it's the sign of b, positive or negative, that causes a reflection or can cause a reflection if it's negative. So for example, just to look at the notation, if a graph y equals f of x is horizontally reflected without also being stretched, and again, we will see today cases where it is also stretched, but if we do it without also being stretched, then that just means every x value is multiplied by -1, right? b is -1. So we multiply every x value by 1 over -1, which is still just -1. And so we could write that transformation as in function notation, right? Y equals f of bx. Well, our b is just -1, right? F of -x. -1 times x is just -x, okay? In mapping notation, same thing. B is -1. We multiply each x by 1 over b, right? So it's 1 over -1, but that just still means our b is -1, right? 1 over b is also -1 then. Okay, and that's what we're doing. Mapping notation, direct instructions on what you're doing to each point. So for a horizontal reflection, what are you doing to each point? You're changing the sign of each x. If it was positive, now it's negative. If it was negative, now it's positive, because a negative would be positive. Okay, let's try this one out. So the graph of y equals f of x is shown to the right. Sketch the graph of y equals f of -x. Okay, so what are we doing here? What can we identify? Looks like b is -1. What's that going to cause? A horizontal reflection across y-axis, right? And more generally, each x is going to get multiplied by -1, right? We could represent this in mapping notation as xy is going to become -xy, every point. So that's all we got to do. Take each point on our original graph, y equals f of x, and multiply its x coordinate by -1 to reflect it across the y-axis. So, whoops, there's a point. Let's just start there. First one I see, -4, -3. Well, if I reflect that across the x-axis, right, where's it going to end up? Sorry, not across the x-axis, across the y-axis. Multiply this by -1, right? It was at -4. If I think of the mirror image here, it's going to be at +1, 2, 3, 4. Right? That will be that one's mirror image for -3. Okay, let's try this one here. Hey, will this one change? It's at 0, 1. What happens if I multiply 0 by negative 1? Well, I still get 0. So reflecting this across the y-axis isn't going to do anything, which actually makes a ton of sense as well because it's on the y-axis, right? It's a y-intercept. So how do you reflect it across the y-axis? If it's already sitting on the y-axis, it just stays put where it was at. So that is what we would call, once again, an invariant point. Okay, let's try another point. I'm just going to use the kind of vertices here, the corners. Okay, I've got this point 3, 1. Multiply the x-coordinate by negative 1. That's what a horizontal reflection in the y-axis does. So this will now be at negative 1, 2, 3, negative 3, 1. And we can start to see the shape of our graph, taking form here. Okay, let's do this last kind of point here. It's at 5, negative 3. So the original point is 5, negative 3. Where's the image point going to be? Negative 5, negative 3. So right there. Whoops. Right here. Negative 5, negative 3. Right? And we can, pull out our ruler, connect it with as straight of line as possible here. Okay. But looks like that is the mirror image of our graph, right? Maybe bold it a bit so it stands out a bit better. You see it? And always the nice thing about these is you can kind of take a step back and check your work, right? Does this look like the mirrored version of the red one? I'd say so, right? It looks like kind of everything has been flipped across the y-axis. This point has ended up here. That's equidistant from the y-axis, right? This point here, equidistant to the y-axis when compared to the original function. So I'd say that looks pretty good. That does look like a reflection across the y-axis. Okay, so now it wants us to describe the effect of this transformation on the domain and on the range of this function. So if we look at our original, right, f of x, what's its domain? You might be able to make some predictions here of how the domain would be affected, but let's just take a look. The original looks like the lowest x ever got was negative 4, and the highest it ever got was 5. So the domain will be the set of all x's such that negative 4 is less than or equal to x, which is less than or equal to positive 5. And x is an element of the real numbers. What about the range? So now we're talking about y values for range. Well, it looks like the lowest it ever gets on the y-axis is negative 3. That's the lowest output this function ever gave us. The highest is 1, so negative 3 to 1. Y is an element of the real numbers. Again, you could also use interval notation. Could say, or negative 4 to 5, or negative 3 to 1. Okay, set notation's more common, but interval notation works too. Now, what about our transformed function, f of negative x, the new domain after doing this reflection? Well, now the lowest x ever gets is negative 5. Right, on our transformed function. The highest it ever gets is positive 4. Okay, so our new domain is the set of all x's such that negative 5 is less than or equal to x, which is less than or equal to positive 4. And x is an element of the real numbers. In our interval notation, we could say that as from negative 5 to positive 4. Okay, now look at that, folks. Compare. Does that make sense? Is that what we would have predicted, right? To go from a min of negative 4 and a max of 5 to a min of negative 5 and a max of 4 for our domain, right? I think that does kind of check out because what have we done? We flipped it across, right? So we've changed the signs of each x and we've flipped them across the axis. Right? So what used to be the highest it ever got, or the most positive value it had on the x-axis, has now become the lowest, the most negative x value, right? And vice versa. What used to be the most negative, lowest x value has become the greatest, most positive x value here. Okay? Makes sense for a reflection. So the domain has essentially gotten flipped around because we horizontally reflected it. What should have happened to the range if all we did was horizontally reflect it? I mean, you can kind of see by looking at the graph, it doesn't look like the range has actually been affected, nor would we expect it to, right? We haven't done anything. We haven't multiplied all the y's by -1. We did a horizontal reflection across the y-axis. So our range is still the same, -3 less than or equal to y less than or equal to 1. Y is an element of the real numbers, or in interval notation, we could say from -3 to +1, right? So describe the effect. That means we should, describe, say what's happened. So our domain, right? Domain was essentially flipped, right? Domain was flipped, so to speak. That's probably not the proper terminology. Domain was flipped because of reflection across y-axis, right? Original Max has had its sign changed and become transformed min for domain, right? Which makes sense. Range, unaffected. We didn't do anything to the y values if all we did was horizontally reflect it across the y-axis. All right, so there we go. There are horizontal reflections. So let's talk, it's come up, right? Let's talk about formally the invariant points for horizontal stretches and reflections. But again, these make sense, right? What are invariant points? They're just points on a graph that when we do some type of transformation, they remain unchanged. So we apply some transformation to a graph and it's not actually going to move that point. It's unaffected. Okay, and again, there's not just one rule for what an invariant point is going to be. It depends on what transformation we're doing. So where those points are going to be depends on what we're doing to each point, right? So we saw, again, when we took the inverse, that was a reflection across the line y equals x. Invariant points were where y equaled x, because all we do there was swap y and x, right? So if y and x are equal, swapping them doesn't change that point. For vertical reflection, vertical reflections and also vertical stretches, what did we do? We multiplied every y value by a. So the points that didn't change were where y was 0, because 0 is the only number where if you multiply it by something, you still get 0, right? You still get the same number. 0 times a is going to be 0 no matter what a is. So similarly, for horizontal stretches and reflections, where are we going to have invariant points? Well, all of the x values are being multiplied by 1 over b. So where are they not going to change? Wherever the x value was 0, because 0 times 1 over b, no matter what b is still going to be 0. So invariant points occur where the original x value was 0, because 0 times anything, still 0, right? No matter what 1 over b is, an x value of 0 will be unchanged when we multiply it by 1 over b, okay? So since x equals 0 is just the y-axis, right, we therefore know that any horizontal stretch or reflection will have invariant points where the original graph crosses the y-axis. In other words, its y-intercepts. So on this page here, or on this little table here, we have a summary of everything we've talked about, the stretches and reflections. Sorry, not everything. Doesn't have translations on here. But we've talked about stretches and reflections for the last little bit. So here's a summary, right? For a vertical stretch, all that happens is each of our y values are multiplied by a factor of the absolute value of a, right? No matter whether a is positive or negative, we can still say it was vertically stretched by that factor. It's just that if it's negative, there was also a reflection that occurred, okay? So in mapping notation, we would show xy has become x a times y, right? In function notation, we show that as, well, y used to be equal to f of x, but now every y value has been multiplied by a. So it's no longer equal to f of x, it's equal to a times whatever our original f of x was. Where do we get invariant points? Points on the x-axis, because that's where y equals 0, and 0 times a is still 0, right? Vertical reflection, the y values are multiplied by -1. In mapping notation, it's really the same thing, it's just that now our a is -1, so xy, a point xy is going to become x negative y. The sign of the y coordinate changes, and that flips it across the y-axis. Again, kind of the same thing here, it's just being a little more specific. For a vertical reflection, that just means our a is negative, right? So y equals negative f of x. Y used to equal something, now it's equal to the negative version of that, right? If it was positive, that means it's now negative. If it was negative, it's now a negative negative, so it's a positive, right? Same invariant points, because it's really the same thing happening. Making 0 negative, it still leaves it as 0, right? Just -0 doesn't really make sense. There's just 0. It's not negative, it's not positive, okay? Very similar for horizontal stretches, except x values are multiplied by a factor of 1 over b, not b, right? 1 over b, again, because of that inverse operation effect, right? We would have to divide both sides by b to figure out what the actual effect on our x's was. So that's why we multiply every x by 1 over b. So in mapping notation, xy becomes 1 over b times xy. In function notation, what we're actually doing is, in the equation, we're replacing x with bx. So y used to be equal to f of x, now it's f of bx, okay? What's invariant to that? Well, points on the y-axis, because there, x is 0. So 0 times anything is still going to be 0. Those points don't move. A horizontal reflection, similar logic to the vertical ones, but now we're multiplying x values by -1. So what used to be a point at xy will now be at -xy, right? Changing the sign of each x coordinate. If it was positive, now it's negative, flipped across the y-axis. If it was negative, now it's positive, flipped across the y-axis. And what are we doing there? We're replacing x in the function with -x, right? We're making b -1. And for the exact same reason, our points on the y-axis, where x is 0, are going to be invariant, because 0 times -1, still 0. All right, so there's our little summary of stretches and reflections. Let's finally put it all together and do multiple transformations. Right, so let's put it all together now, folks. That's all we're going to do here, okay? We're going to take all the pieces that we've talked about and put them all together. So far, we've only done one or the other, right? We've only done transformations one at a time. We might have done a translation or a stretch or a reflection. But realistically, all of these transformations can be performed to a function. Everything's the same. Nothing's going to change here. The ideas in the steps is everything we've talked about. We're just going to put them all together, right? We'll first do a we'll talk about the order here, but we'll do the same things we've been doing. We're just going to do them one at a time, right? We have to do multiple things, but we'll do them one at a time, okay? So this is very important, very, very important, and it makes sense. It's not just some magic rule. Remember, when we do a translation, when we slide it, what are we doing? We're adding or subtracting something to each x or y value, right? Horizontal translations add or subtract something to x with h. Vertical translations add or subtract something to the y's with k. Okay, and then we saw that stretches and reflections are multiplying x and y by something, right? In a horizontal stretch, every x value gets multiplied by 1 over b. In a vertical, every y value gets multiplied by a. So we're doing those operations. We're multiplying and then we're adding and subtracting. So we need to follow, like we always do whenever we do any type of operations, we need to follow the order of operations, right? BEDMAS, or some people say PEMDAS. I'm not sure which one you learned, okay? Most people, I think, go with BEDMAS. Okay, so we need to follow the order of operations when applying those transformations. So what does that mean needs to be done first? right? If these are multiplication, well, BEDMAS, right? Multiplication comes before additions and subtractions. So we need to do reflections and stretches, those are multiplications, before we do any translations. Those are additions and subtractions, okay? We will actually get the wrong graph from what we were trying to get. We won't actually be doing the transformation that was described to us if we first translate and then stretch or reflect, okay? Sometimes you can use this if you like. They sometimes say RST to help us remember the acronym RST, just because it's alphabetical, right? LMNOP, okay? Sometimes we use that to help us remember the order: reflections, then stretches, then translations. But truth be told, both reflections and stretches are multiplications, right? So the order of these two doesn't actually matter. You can stretch, then reflect, or you can reflect, then stretch. But these two must happen before you translate, okay? Those are both multiplication. So those need to happen before you add or subtract with a translation. Okay, so RST is a nice way to remember. Reflections, stretches, translations, not translations before reflections or stretches. Okay, so let's just review what we saw individually for each of these, for translations, for stretches, and for reflections. Okay. The function notation, remember, that showed us, generally speaking, what are we doing to the original function with this transformation, right? So for a vertical translation, we're adding something to all the y values. So y was equal to f of x, but we're going to add k to it. You sometimes see it written this way too. Personally, I prefer this. It just feels a little more intuitive, but sometimes you do see it as y minus k equals f of x. You can see that if we just add k to both sides, we get this one, okay? So that's just showing us, again, y was equal to just some equation, f of x. Now we've added k to every y value in order to translate it up. So now y is equal to the original equation, f of x, but add k to it, right? In mapping notation, more direct, telling us exactly what's happening to each point. So an original point x, y will become x, y plus k. We're going to add k to each y value to shift it up or down by k, depending on whether k is positive or negative. Okay. For a horizontal translation, we're doing that to the x's, to the inputs, right? We're altering the inputs, the horizontal translation, the x's. Okay, so before it even goes through the function, we're altering what we input. So this one we represent as y equals f of x minus h. We're changing the inputs here. X minus h instead of just x. Still a similar idea. It's saying, how do we translate this graph horizontally? Well, it's going to look a lot like y equals f of x, except instead of being f of x, it's f of x minus h. Notice how we're not subtracting h from the whole equation. We're changing our input. We're replacing x as the input with x minus h as our input. What effect does that have? We know that h, right? H, if I have x minus 1, for example, that means my h is positive 1, so it's shifted to the right by 1. If I had x plus 1, that would mean my h was negative 1, x minus negative 1, so I'm shifting it to the left. So in mapping notation, right, a positive h moves it to the right. We are adding that number to x. A negative h moves it to the left, so we would have still x plus h, but h would be negative there. So again, more direct, showing us exactly how we change each point, right? x, y is going to become x plus h, y, okay? Vertical stretches or reflections, we multiply every y value by a. So again, same idea, we take the whole function equation, y used to just be equal to f of x, whatever that equation was, but we're going to multiply all those y values by a. So multiply the whole thing by a, right? So x, y has become x, a times y, right? Whatever point we were at, now the y coordinate has been multiplied by a. And for a horizontal stretch or reflection, again, we're not transforming the y's here, so we don't want to multiply the whole equation by b or 1 over b. We're affecting the inputs. Instead of having x as our input, right, this is going to look like the graph of y equals f of x, but instead of f of x, it's been replaced with f of bx. Okay, so bx is our new input. And again, in mapping notation, we show directly what that means for each individual point. So each individual point x, y will have become 1 over b times x, right? That will be the new x coordinate. again, comes from that inverse operation thing. If I replace x with bx and then I want to find the effect it had on the x's, I would end up dividing both sides by b to figure that out, okay? So this is a summary of all of that stuff. If we put them all together, right, here's what we get, okay? This you will find on your formula sheet. It's very handy because it shows us to do any transformation. Notice, we could do a vertical stretch or reflection or both, a horizontal stretch or reflection or both, a horizontal translation, a vertical translation. We could do all of them and we could represent them conveniently this way. And all this is telling us, right, it's showing us how we would need to alter the original equation. So if we had y equals f of x to start with, that's our original equation, right? The graph of the transformed function, or the equation of the transformed function, is going to look like y equals f of x, but changed in these ways. Which ways? Well, instead of f of x, we've replaced it with b times x minus h, right? And then we've multiplied the result by a, and we've added k, right? So you can see there's kind of like this inner stuff, the input stuff. What is happening to x, the horizontal stuff? That just replaces x in the original equation. And then since y are the outputs, we do it to the whole equation. We multiply the whole thing by a and add k. Okay. In mapping notation, same thing. Notice this is just taking all of these, right? Say this was taking all of these and putting them into one big thing, right? Subtract h from x, multiply by b for function notation. Okay, then multiply f of x by a and add k to f of x. It's just doing all of them at once. So similarly for mapping notation, right? X gets multiplied by 1 over b and then gets h added to it. So we're just doing both of them. We're showing that what happens to each x? Well, first it gets multiplied by 1 over b, and then we add h to it if we did a stretch and a translation, right? For y, well, a vertical stretch, we multiply the y by a, and then for the vertical translation, we add k. So do both of those, you get that y becomes a times y, right? Multiply it by a, and then add k. So that's just taking all of this and putting it into one spot. I know it kind of looks like a lot, right? I know this maybe looks a little intimidating, but it really is just all we've talked about in one spot, right? So there it is. If we are given an equation for a transformed function in function notation, so again, this is in terms of the original function. It's saying here's what you would need to do to our original f of x to get the transformed one, right? You would need to take its original equation, replace x with b times x minus h, where b tells us the horizontal stretch will be by a factor of 1 over whatever we see there, okay? And also a reflection if the b is negative. H will tell us the horizontal translation, h units left if h is negative, or right if h is positive. And then we're going to take that equation, f of bx minus h, right? That kind of takes care of the horizontal stuff. And for the vertical stuff, we would multiply it by a, right? Multiply the original equation by a and add k, right? For the vertical translation. Okay, so it's everything put into one convenient spot. We built up all the pieces, now we've finally put them together. Let's see if we can pick out the transformations that are happening to some graphs when they give us their equations in this function notation, the transformations represented in function notation. So again, this isn't like the equation that you could graph, right? It's got an f of 2x and we don't know what f is. What it is, though, is a description of how we would need to alter y equals f of x to get the transformed equation, and therefore the transformed graph if we did graph that transformed equation, okay? So just we'll have it up here for reference so we can pick out the stuff we need to pick out, okay? We've got y equals 3f of 2x plus 5. So let's start, right? How does it look different from f of x? Well, we've got this 3 being multiplied. So pick out your parameters. That's my advice, right? First, pick out the parameters. So what is this 3? The 3 is a. A is 3. What does the parameter a cause? A vertical stretch, right? So we've got a vertical stretch going on. Let's just pick them out first, then we'll think about what's actually happening in the order we need to do them. Okay, what about this? Where is this? This is being multiplied by our x in terms of the input, right? We've replaced x with a 2x. So that is my b, right? We're not subtracting or adding anything to the x here. We've got 2x. We've replaced x with 2x. So it looks like b equals 2, okay? And then we've got 3f of 2x. We're adding to it 5, right? Outside of, it's not part of the input. It's not 2x plus 5 in here. It's plus 5 to the f of x stuff, right? So that is our k. Our k is positive 5. Okay, so if we think about that, right, what does this mean in terms of the transformations? And we got to be careful about order here. Don't forget, RST, right? Reflections and stretches must come before translations. That's just the order of operations. So, doesn't matter the order, but we must deal with A and B before K. This is a translation. These are both stretches. Okay, so let's write out the proper terminology. So, we could, we have to do these two first. So we would do a vertical stretch by a factor of 3 about the x-axis. Okay, that would be our first thing. And again, then we would do a horizontal stretch by a factor of, be very careful, is it going to be a factor of 2 for a horizontal stretch? If b is 2, is the horizontal stretch 2? No, right? It's always 1 over b for the horizontal stretch, again, because x isn't actually isolated in those equations. So it's a horizontal stretch by a factor of not 2, but 1 over 2 about the y-axis. So now we've done our stretches. Again, we could have flipped the order of those. It doesn't actually matter which stretches you do first, as long as all stretches and reflections are taken care of before any translations. So then, and I'm going to emphasize then because it has to come after, then a vertical translation, because K causes a vertical translation. We're adding 5 to all the y values. So a vertical translation of 5 units up. And there we go. That is what we would need to do. Vertically stretch by a factor of 3, horizontally stretch by a factor of 1/2, and then vertically translate 5 units up. Okay, moving on to this one here. Now notice, this one doesn't quite look the same as the version that's on our formula sheet, right? It looks slightly different, so be careful. That's how they can try to trick you, right? We're not, the k isn't -2, right? If we were to rewrite it in this form, we would see that, okay, if I added 2 to both sides, I'd have a +2 over there as my k. So always, I recommend, try to write it so it's in this form. This is the form on your formula sheet. It's a little more intuitive to think about, I think, anyway, and you can kind of more easily compare to what you've got there. So I've got y minus 2 equals that. First things first, let's just, y is isolated in our function notation, so let's isolate y. I'm going to add 2 to both sides, and then I'll have y equals f of -3x plus 6, and now I can see, okay, that +2, that's really just kind of my k value, right? We're adding 2. Now another thing, they're really trying to get us here, because look, -3x plus 6, is that in this form? Not quite, right? B is supposed to be getting multiplied in that form by the whole thing. So our h, this is tricky, our h is actually not going to be 6, right? It's supposed to be -3 times x plus something, right? I mean, we can probably work out what something should be, but, right, it's b times x minus h, not bx minus h, not b times x and then minus h from that. It's x minus h and then that's being multiplied by b. So how can we do that? How can we make it look like this? Well, notice we have 2 terms here. If I factor this out, right, if I factor out that -3, well, then it will look like that. I'll have, let's just do it, I'll have y equals f of, let's factor that -3 out. So remember, factoring essentially means I'm going to pull out the thing that both of these can be divided by, right? Really what that means is I divide each of them by -3, and then I multiply by -3 outside of the brackets, and it leaves us with something simpler inside the brackets, right? Essentially, divide each of these by -3, and then since we can't just divide by -3 because we want to, right? We have to cancel that out by multiplying by both of them by -3 outside of the bracket. So I'm going to factor -3 out of each of these terms. So -3x divided by -3 is just leaving me with x, and then a +6 divided by a -3, plus 6 divided by -3, that's -2. And we can tell that we factored this correctly, right? You can always check your work for factoring by unfactoring or remultiplying them, right? We sometimes say factoring's like unmultiplying. What two things could have been multiplied together to give us this, right? Well, -3 times x minus 2, is that equivalent to this? Sure enough, -3 times x would be -3x, and -3 times -2 would give me that +6 term. So we factored this correctly. And the reason that was so helpful is that now look at this. Compare this to this, right? We can now pretty easily pick out our b is actually -3. Our h is +2. Our k is +2. What would a be here? Well, a is just 1, right? In other words, no vertical stretch, no vertical reflection is happening. Okay, so let's pick it together. Now remember, RST, reflections and stretches must happen before translations. So we've got reflections, we've actually got stretches as well, and we also have translations. So I don't see any vertical stretch. Like we said, it looks like A is 1, but I do see a horizontal stretch, okay? So we've got a horizontal stretch by a factor of, careful, not 3, 1/3 about the y-axis, 1/3, right? Anything else happening with our b value here? It is, we are multiplying each x by 1/3, but really -1/3. So what's that going to cause? It's going to cause a reflection across the y-axis, right? We're making each x value have the opposite sign by multiplying it by not just 1/3, -1/3. Okay, so have we dealt with all of our reflections and stretches? Yes, I think so, because we only had horizontal reflections and stretches happening here, no verticals to worry about, and we've talked about the horizontals. And then what does k do? K is going to cause a vertical translation 2 units up. Okay, and again, that just came from, how did I figure that out? B is -3, so our horizontal stretch is -1/3. The negative part gives us that reflection, and then K is +2. And there we go. So just pick out your parameters one at a time and then deal with them in the correct order following the order of operations, RST. All right, so let's try out this one here. I'd encourage you, go ahead, pause the video, see if you can pick out A and or B and or H and or K, right? Not saying all of those are necessarily there, but I see a few of them. Okay, see if you can work ahead of me. But I'll go ahead and take a look at it now, right? Again, nice to have this, written down, or at least have, if you don't have your formula sheet next to you, at least have it written down somewhere whenever you're working with these, because it's nice to be able to compare to the general function notation. So you can kind of pick out, this is my A value, my B, my H, my K, right? So we're always working with, in function notation, we're saying that the transformed equation looks like f of x, except that equation has been multiplied by A, x has been replaced with a b times x minus h, and then the equation has had k added to it, right? So looking back and forth between that and the one you're working with can help you pick out those a, b's, h's, and k's a little more easily. So looking at this, I noticed that, all right, it looks like we're multiplying the f of x stuff by 1/2. So that must be my a, right? A looks like is 1/2. So we know we're dealing with a vertical stretch by a factor of 1/2 about the x-axis. What do we got here? That looks like a B to me, right? Now B is 2. which means we've got a horizontal stretch by a factor of not 2, that's right, 1 over 2, right? A horizontal stretch by a factor of 1/2, but our b value is 2. Doesn't look like we have an h here. I mean, if you wanted, you could say h was 0, right? H equals 0. And then k, what's in k's spot? Looks like a positive 1, right? So k is positive 1. Okay, so let's think about what that's going to do to each point. It wants us to use mapping notation. Mapping notation is often very handy when we're trying to, sketch the graph, because what it is it's instructions on what to do to each point. So in general, if we have some point on our original graph, x, y, what is going to happen to that general point if a is 1/2, b is 2, and k is 1? Well, again, in general, mapping notation, what do? We start with a point x, y, and we end up with, careful, we multiply every x value by 1 over b. We then add h to it, right? If h is positive, it ends up moving to the right. If h is negative, that really means we're subtracting that number, and it ends up moving to the left. X plus h, and then same thing for the y's, except we multiply every y value by a, and then we add k to it, right? So in general, that's what we're working with. That's the general mapping notation, how points are transformed. So for us here, our a is 1/2, our b is 2, and our k is 1, right? So let's just focus on the x's first. What is going to happen to x? Well, x is going to get multiplied by 1 over b. So x is going to become 1, whoa, what's going on there? 1/2 x, and then plus h, but our h is 0, right? So really all that's happening to our x's is this horizontal stretch. Every x will be multiplied by 1/2. And our y's, well, there's an a and a k. So every y coordinate is going to get multiplied by a by 1/2. So our new y will be at 1/2 y, but then also have k added to it. So also plus 1, right? And that's in general how each and every point on this original function's graph, like these ones, is going to get altered. So now what we can do is we can go through each point and say, all right, well, where will that end up if these things happen to it? Where will this end up if these things happen to it, right? So 0, 0 is going to be now at 1/2 times 0. And then the 0 will be at 1/2 times y, which for this point is 0. Its y value is also 0, plus 1. Okay, so I'll just do another arrow there just to show. So what does that give us? What's our new point? Well, 1/2 of 0, 1/2 times 0 is still 0. And then 1/2 times 0 here is still 0, but plus 1 is now 1. So there we go. We've got a point on the new transformed graph. Our transformed graph should have a point at 0, 1. And that just came from transforming one of the points that we knew it had originally, 0, 0. So the corresponding image point we now know is at 0, 1. So the video got cut off there, but what I was going to say is, so let me add that point to the graph, right? We know this is on our image graph, so 0, 1. Careful, always check how the y-axis and the x-axis are scaled here. 0, 1. So there's our first point on our image graph. And now we're just going to do the same thing for the rest of these points, folks, right? I mean, this one, they've given us the coordinates. We could have also just picked them off the graph ourselves, but they're just getting us to really think about our mapping notation here and how helpful it can be. So we're going to do the same thing. The x values all get multiplied by 1/2 because b is 2. Horizontal stretch by a factor of 1/2. Whoops, my new x coordinate is not 0, sorry, it's 1. So we're going to do 1/2 times 1. And then the y coordinates get multiplied by 1/2 because there's a vertical stretch by a factor of 1/2. So our new y coordinate for this point is 1. And then they get vertically translated 1 up. So we add our k of plus 1. So what's that going to become? Well, 1/2 times 1 is 1/2. 1/2 times 1 for our y coordinate is 1/2. Plus 1 is 1.5, or, 3 halves, right? Could work in decimals here as well. In fact, I might, just because, I don't know, for graphs sometimes it's a little easier to think about where 0.5 and 1.5 are. and these are just halves, so they make nice decimals, not repeating decimals. But anyway, we've got 0.5, 1.5. So be super careful with the scaling. This is a tricky one because the x-axis scaling is actually different than the y-axis scaling. On our x-axis, every square on the grid represents 1, right? 1, 2, 3, 4. Whereas on the y-axis, every square actually only represents 0.5, right? 0.5, 1, 1.5, 2. So we got to be careful. If this is 0 and this is 2, then this is 1, and this is 0.5. So our x is 0.5, and our y is, if this is 1 and this is 2, then this must be 1.5. So that is our second point. This would be 0.5, 1.5. And we keep going. So 4, 2. Every x coordinate gets multiplied by 1/2. B is 2. We have a horizontal stretch by a factor of 1/2. So 1/2 times 4. And then every y coordinate gets multiplied by 1/2 because A is 1/2. Vertical stretch by a factor of 1/2. So 1/2 times 2. And every y coordinate then gets 1 added to it because we have a vertical translation, 1 unit up, a k value of 1. Okay, so what's our new point here going to be? Well, 1/2 times 4, 4 divided by 2 is 2. And 1/2 times 2 is 1, plus 1 is 2. So the point that was originally at 4, 2, this point here, we can now see is going to end up at 2, 2. So x is 2, y is 2 for that point's image point. Right around there, 2, 2. One more to go. Every x coordinate gets multiplied by 1/2, so 1/2 times 9, okay, and then we've got an a value of 1/2, so each y coordinate gets multiplied by a, and then a k value of 1, a vertical translation 1 unit up, so add 1 to that, and what are we going to get here? Well, 1/2 times 9 is, 9 over 2, you could say, or we could just say 4.5. Might just go to decimals here for thinking about it on the graph. 1/2 times 3 is 1.5. 1.5 plus 1 is 2.5. And so that point that was originally at 9, 3 is going to end up at 4.5. So 4, there's 5. So 4.5, 2.5. Right there. 4.5, 2.5. And be careful here, right? We don't want to notice this didn't extend that way. It wasn't saying that the domain continued on above, right? And same thing over here below, or for the range for that matter. So this can't either, right? We can't say, oh yeah, now it extends to all real numbers, right? Yes, the domain and the range has changed because the graph has definitely been messed with, but it's still kind of following the fact that this was the endpoint, this was the endpoint, right? We've just shrank it down and then translated it up. Shrank it both vertically and horizontally in this case. And there we go. We used our mapping notation to think about what happens to each xy point on the original graph, and then we just did that for each point to figure out where the new points would be. Could have done it with the graph as well, although when we have these multi-step ones, it can be a little confusing to keep it all in your head of like, oh, okay, I got to multiply this by 1/2, then I got to multiply this by 1/2 and add 1. This is where mapping notation kind of shines because we can just quickly write out what the instructions are essentially for each point and then do it to the points without, losing stuff if we try to do it in our head. But there we go. All right, let's take a look at this next one here. So they're saying that the graph of the function y equals g of x is just a transformation of the graph of y equals f of x. So in other words, this graph here, this red one, is just the result of performing some transformations to this one, or at least we can obtain the graph of g of x by performing some transformations to the graph of f of x, right? And then it wants us to determine the equation of g of x in the form y equals a f of bx minus h plus k, right? So essentially, write the transformation, represent it using function notation. We don't actually have to come up with the equation of g of x itself, but we need to come up with the equation of g of x in terms of f of x, right? This function notation shows us how g of x is like f of x if we make some changes to the equation of f of x, right? Replace x with b times x minus h, multiply that by a and add k. All right, so typically a good strategy with these, especially when we know or suspect that there might be stretches and translations going on, okay? Not always the case, but like often if we can figure out any points that shouldn't change due to stretches or reflections, that can help us focus in on what the translations might be, right? So I'm not saying there's one right way to do this, but that's often a good place to start because we know that first any stretches or reflections would have been performed. So if there's any places that would still be, any points that would still be in the same spot once we did those stretches and reflections, and those points are not there, well, what's left for them to have been moved is only translations, right? So let me show you what I mean here, okay? Because it's totally possible that this was stretched and reflected and translated. And how do we figure out which ones of those happened? Well, I'm noticing that this parabola, I mean, we can tell this is just y equals x squared, right? Now, it passes through the origin. It passes through 0, 0. And what's special about that for us here, or what's helpful about that for us here, is that this shouldn't change from a vertical stretch, from a vertical reflection, or from a horizontal stretch, or from a horizontal reflection, right? So if this graph was horizontally or vertically stretched or reflected, that point 0, 0 should still be there, right? Because again, in a vertical stretch or reflection, what do? We multiply the y coordinates by a. So if this was at 0, multiply it by a, it should still be at 0. And same for the x coordinates getting multiplied by 1 over b. Because if this was at an x coordinate of 0, 0 times 1 over b, it should still be at 0. Now, obviously, that point did not stay there, right? On our new graph, the vertex is here. So do you see what I mean? We know that, okay, it's totally possible that a stretch, multiple stretches and multiple reflections could have occurred here. However, we can see that once we did any type of stretch or any type of reflection, this point would normally still be there. So what could have moved it to here? Well, all that's left is a translation, or rather two translations, a horizontal translation to here and then a vertical translation to there. Do you see the logic there? It's often nice if you can see any points that would be invariant to one of the transformations you're doing and it still got moved. That kind of lets you think about what the other transformations would have to be. So often I like to first think, okay, are there any points that would be invariant to a stretch? Because that way I can say the stretch happened, but I still know that point should be there, right? So vertical stretch could happen, point would still be there. Horizontal stretch could happen, point would still be there. So how did that point end up over there then? Well, all that's left to explain that is that it was horizontally translated 3 units right? Horizontal translation 3 units right. And then from there, a vertical translation 1, 2, 3, 4 units down. Okay, so what does that tell us, right? We're basically trying to fill in what are h, k, a, and b in order to write this equation in, function notation. Well, we now know that it was horizontally translated 3 units right, so our h is what? It's positive 3. And our k, if it was translated 4 units down, well, k must be negative 4 then. Okay, so 2 down, 2 to go. We figured out k, we figured out h. Now let's see if we can start thinking about the stretch. And again, does it have to be in this order? Not necessarily, but I often like to go with, if you can figure out a point that would be invariant to the stretches, that kind of lets you focus on what the translations might be. Okay, and in this case, we could do that. So that worked out nicely for us. Now let's start thinking about stretches. Another thing to point out here, typically when a question or, a question, I guess, or a graph from your book or from maybe the diploma, what it's doing by highlighting these points, notice how it made certain points like kind of bolded and stand out. What it's showing us that's what they're trying to communicate is that these are corresponding points. So these 3 points here correspond to these 3 points here. Right? The reason they're highlighting that is that allows us to think about how has this been stretched, okay? So if we take a look You might recall this is actually what we did in Math 20 to think about vertical stretches, the parabolas, how they had been stretched. Now we're just adding in horizontal stretches as well. So if I take a look here, notice something. Notice before on the original graph, we kind of go over 1 from the vertex, up 1, right? Over 1, up 1. Or we could go over 2, up 4, over 2, up 4, which makes sense because that's the graph of y equals x squared, right? So starting from the vertex, if I go 1 away on the x-axis, I should go up 1 on the y-axis because 1 squared is 1. If I go 2 away on the x-axis, I should go up 4 on the y-axis because 2 squared is 4, right? That kind of thing. But I'm pointing it out here because look, over 1, up 1. Let's see what this one does. How does it get to the corresponding point here? Well, here, in order to go from this, right, it used to be to go to this point to that point, you had to go over 1, up 1. Now we have to go over 2, down 3, right? Over 2, down 3. Over 2, down 3. And again, the reason I'm confident that that is meant to be the corresponding point is because of the way they've kind of emphasized it with these 3 dots here, right? They're saying these 3 points correspond with these 3 points. Okay, so over 2 and then kind of down 3. What else do we notice here? It looks like, has a reflection occurred? And if so, in which axis? That's right. This looks like it has definitely been reflected across the x-axis. Now, you might be saying to yourself right now, or, screaming at me through your screen, how do you know it wasn't horizontally reflected too? You're right. There is technically a way to write this equation where we reflected it horizontally. The thing about a parabola here is that a parabola actually it doesn't look like it's changed when you've taken a reflection of it in the y-axis, right? Because parabolas, one of their key characteristics is that they're symmetric about the y-axis. So reflecting that point over there, it ends up making our graph look similar. It's not actually invariant because we still did move those points, but the graph itself ends up looking the same. So all of that to say, there is actually more than one correct answer to this question. There is more than one thing you could make B. If you make B -1 right off the bat, you could still find the correct equation for this. In fact, there's more than one correct combination of A and B that could give you this graph, because the thing about something like a parabola is that when you vertically stretch it, you also change its horizontal dimensions, right? We've seen that before. If I vertically stretch the parabola upward, it kind of gets narrower. Well, same goes if I horizontally stretch the parabola with an B value that's, going to make it narrower. So technically there are multiple combinations of A's and B's that could make this correct. So there's not necessarily one right answer. What I'm going for here is basically the most, the answer they're leading us to the most by pointing out these corresponding points. It's not actually going to be the one and only correct way we could look at transforming y equals f of x to get y equals g of x. Okay, I'm basically picking out the one that they're trying to get us to go for by highlighting those points. So let's take a look here. It used to be it went over 1, up 1. Now it goes over 2, down 3. You can almost think of it as like a run of 2, a rise of 3, although that's not quite the correct term since we're not talking about a line with a constant slope, okay? So how do we make something so that instead of going, having to move 1, we're having to go 2? It's like it's twice as wide, right? What would we have to multiply all the x's by to get that? Well, we would have to multiply x's by 2, right? To make this parabola kind of twice as wide, we'd have to multiply our x's by 2. So a horizontal stretch by a factor of 2. What does that mean for b? What is b? Careful. That means b is 1 over 2, right? So there we go. 3 down, 1 to go. Now our a value ties back to what I was saying earlier. It's been vertically reflected across the x-axis. Right? The y values have had their sign flipped. They were all positive before, except for 0. That was 0. Now they're all negative, right? Every y value has been flipped across the y-axis. We can across the x-axis. So a, whatever it is, a we are predicting to be negative. That's how we get a reflection across the x-axis. But negative what? Well, look, to get from this point to that point, we used to have to go up 1. Now we have to go down 3, right? So it used to be this was like 1 unit tall and 1 unit wide. Now the same kind of distance from corresponding point to corresponding point, it's 2 wide and 3 tall, right? 1 wide, 1 tall, 2 wide, 3 tall. So we took care of the 2 wide part. It's been horizontally stretched by a factor of 1/2. And now we can also see it's been vertically stretched. It's now like 3 times taller, right? The y's must have been multiplied by 3. So our vertical stretch was by a factor of 3. And therefore, what is our A? Our A is -3, right? This tells us that the absolute value of A is 3, but we know that it's actually, sure, the absolute value is 3, but A is actually -3 because there was a vertical reflection across the x-axis that also happened. So now, we've got all the parts, right? We've got A, we've got B, we've got H, we've got K. So we can write the equation for this transformed function. Y equals A, we now know that our A is -3. F of B, we know that B is 1/2, x minus h, so x minus 3, plus k. So plus -4 is -4. And there we go. That's the equation for g of x in terms of f of x. It's saying if we knew the equation for y equals f of x, which we actually kind of do, we can tell it's y equals x squared, right? If you changed it in these ways, you would end up with the equation for g of x, right? Replace x with 1/2 of x minus 3, multiply the result of that by -3, subtract 4. But there we go. We've now written the equation in function notation for the transformed equation. Right, and here's one that comes from a diploma, okay? So if the point A, -3, 4, again, don't get thrown off by that A there. All that's saying is that that's the name of the point, okay? Is a point on the graph of y equals f of x. Then where will the corresponding image point, A prime, be on the graph of y equals 1/2 f of 3x plus 12 minus 1 be, right? We're given these options. Okay, so fundamentally, what does this question boil down to? Well, can we interpret function notation, pick out A, B, H, and K, and then successfully apply the transformations associated with A, B, H, and K to this point? Figure out where would the x-coordinate end up, where would the y-coordinate end up, right? So let's start at the beginning of what we just laid out, right? Can we pick out in the first place, can we interpret function notation to pick out A, B, H, and K? Well, function notation, it is given on your formula sheet. It's y equals A f of B times x minus h plus k, right? So let's compare that to this. Now be very careful. They're trying to trick us again. Right? Do we notice anything? Does this look right? Does this look quite like function notation? Not quite, right? It's not supposed to be bx minus h. It's supposed to be b x minus h. So how can we fix that? Well, once again, right, whenever this is the case, what we need to do is just have x minus h, know a coefficient on our x. So we can fix that by factoring out whatever this coefficient is. So let's do that as our first step here. We're going to have y equals 1/2 f of, and I'm going to factor 3 out of this, right? So again, that just means essentially we're going to multiply by 3 so that we can divide each of these by 3. And worked out here where they're both divisible by 3, so that'll work out nice. So that means what am I left with? Well, 3x divided by 3 is x, 12 divided by 3 is 4. Just factoring a 3 out of those terms, those two terms, right? And we can always double check that we factored correctly by trying to multiply the 3 back in. We'd have 3x plus 12. Oh yeah, that's what we started with. So we factored this correctly. Minus 1. Okay, that minus 1 there. All right, Now this is a little bit easier to pick out our a, b, h, and k, right? Compare to function notation in its general form. See what you've got for an a, b, an h, and a k. Looks like our a is 1/2. So we got a vertical stretch by factor of 1/2. Every y value is going to get multiplied by 1/2. What's b? What's b? Do you see it? Looks like b is 3. So what's the horizontal stretch? Very good. It's 1/3, 1/3, right? Kind of backwards for the horizontal stuff. But again, not really backwards when we understand why. It's just because x isn't isolated in these equations. So hs by factor of 1/3, horizontal stretch. What's h? Is it 4? Good, not quite. H here is -4, right? Because it's supposed to be x minus h in function notation. So it must be a -4 so that x minus -4 got simplified to x plus 4, right? And again, that comes from the fact that x is not isolated. If we were to isolate for x, we'd see that, we end up subtracting 4 from each side. And our k is -1. So this gives us a vertical translation, 1 unit down. This one gave us a horizontal translation, 4 units left. Okay, so we've picked out our a, b, our h, and our k. We've thought about what those transformations mean, right? And now, honestly, this is one where I think mapping notation would be very helpful. Do we need to? No. I mean, we know what's happening to our x's and we know what's happening to our y's, but mapping notation can be really nice for just thinking about, making sure we don't miss anything, especially in terms of orders of operation, right? Make sure you're doing multiplications, stretches, before additions and subtractions, translations, okay? But I'm just going to write the mapping notation so we can have a kind of a clear image of what we're heading into here. Every point on that graph, whatever that graph was for y equals f of x, is going to become x, y, right? It's going to get multiplied. The x coordinate's going to get multiplied by 1 over b. So for us, that's 1/3 x. And then it's going to have h added to it. Now our h is -4. So adding -4 means we're going to do 1/3 x minus 4. Now what's going to happen to the y coordinate? Well, anything vertical, right? Vertical affects y. So a is 1/2. That's a vertical stretch of 1/2. Every y value gets multiplied by 1/2 then. So 1/2 y. And then a vertical translation 1 unit down. So every y value has 1 subtracted from it. Whoops, that's the wrong color. -1. Okay, and there we go. Those are instructions on what to do to every single point. We are just interested in a specific point, the point A that started at -3, 4. So what are we going to do to it? We're going to multiply its x coordinate by 1/3. So 1/3 times -3. And then we're going to subtract 4 from that. Horizontally translate it 4 units left. Then what are we going to do to the y coordinate? Well, we're going to multiply it by a, 1/2. So 1/2 of 4. And we're going to subtract 1 from it to translate it 1 unit downward. Okay, and now we just got to do the math on that to figure out where -3, 4 actually ended up. So 1/3 of -3 is -1, right? 1/3 times -3 is -1. -1 minus 4 is -5. And then for this one, 1/2 times 4 is 2. 2 minus 1 is +1. So it looks like our point ended up at -5, 1, which is option C. Hey, we got it, right? So just using the function notation to tell us what transformations occurred, and then applying those transformations following RST, the order of operations, right, to that specific point. And there we go. Go ahead and give this one a shot. It's a nice little fill-in-the-blank one, right? And again, take some time to practice this and get comfortable with it. Or again, you can save that for later if you want to do all your practice later. But I recommend breaking it up into little chunks, getting comfortable. And once you're comfortable, we'll move on to transforming equations, which we've really kind of been talking about, but we'll really jump in and do it now for real. Right, so let's transform the equations now. And again, we really have been doing that all along and we've been making reference to it, but now let's actually see how it looks when we do it, okay? So any transformations you're doing to a graph, you're also doing to its equations, right? I mean, that's why its graph is changing. The reason that y equals x squared, right, looks like this, and y equals x squared plus 1 looks more like this, it's been shifted up by 1, is because they have different equations. Different x and y points will satisfy this equation than this equation, right? Here, all the y values are equal to not just x squared, but x squared plus 1. Whereas here, all the y values are just equal to the x values squared, right? And that's why this has all been shifted up by 1. Every y value compared to this one has been moved up by 1. So when we're transforming graphs and transforming equations, really we're doing both, right? To change something's equation is to change its graph, and vice versa. The only way to change a graph is to change that equations, equation, okay? So a function's equation, f of x equals, blank stuff, just tells us what the inputs are and what the function will do to those inputs to get an output, right? Don't forget, that's what a function's all about. Tells you what inputs you're putting in, tells you what outputs you're gonna get out if you actually put in those inputs and evaluate. So when we apply transformations, they could affect our input x's, right? Kind of before we even send them through the function, we could change what we're going to input, those x's. That's the horizontal stuff. X is horizontal. So a horizontal stretch or reflection from B, right? A horizontal translation from H. But of course, we've seen transformations can also affect our output y's, right? They might affect the input x's, but they can also, vertical stuff can happen. We might get a vertical stretch or reflection from A, or a vertical translation from K, or again, both, okay? So let's focus in on these one at a time. Transformations done to x just replace x as the input in the original function equation, right? In order to produce the transformed equation, literally what we're doing is we're replacing x with b times x minus h, right? That's why in our equation we've got that, the transformed one will be a times f of b times x minus h, right? Remember, that's our input. This is what we're inputting into the function. For f of x, what are we inputting? X's. F of 3 means we're inputting 3, right? So f of bx minus h means now we're going to input b of x minus h. That's why it's written this way. It shows us, again, function notation shows us, it acts like instructions on how to transform the equation. The transformed equation is going to look like f of x, but you have to replace x with b times x minus h. Then multiply it by a and add k, but we'll get to that in a second. So for example, suppose we wanted to horizontally stretch this linear function, f of x equals x plus 4. So we wanted to horizontally stretch it by a factor of 1/2, meaning our b is 2. And we wanted to move it 5 units to the right. So h is 5, right? Horizontal translation, 5 units right. Then what is b times x minus h? Well, b is 2 and h is 5. So b times x minus h is 2 times x minus 5. So in order to transform y equals f of x into this new functions equation, this transformed functions equation, what this is literally saying is take f of x, but instead of having f of x, have f of 2 times x minus 5, b times x minus h, right? That's what we're doing. We're just going to replace x with 2 times x minus 5 wherever we see x in the original equation. Because we no longer want f of x. We want f of 2 times x minus 5. That's what's so handy about function notation. It's instructions on what to do to the equation to get the transformed equation. So we used to have y equals x plus 4. Now, wherever I see an x, I'm going to make this the input. 2 times x minus 5 plus 4. And then we can simplify this out, right? So 2 times x, 2 times negative 5 gives us 2x minus 10. And then collecting that negative 10 and 4 as like terms gives us overall, y equals 2x minus 6. And there we go. This is the equation of the transformed function. So sometimes students get hung up here. They say, I thought this was the equation of the transformed function. And they're not wrong, but this is the equation of the transformed function in terms of f, right? This is still relying on us knowing what f is, so to speak. It's saying it's like f, but you have to make these changes. It's still referring back to f. This is just straight up the equation for our transformed function, right? This, if I graphed y equals x plus 4, and then I graphed y equals 2x minus 6, I would see that this one looked exactly like this one, except it had been horizontally stretched by a factor of 1/2, and then shifted 5 units to the right, okay? So that's what we've come up with here now. This one requires us to still refer to f. This doesn't. You could put this in your calculator and graph it, or even graph it by hand. Okay, so that's the difference between these two. This is in function notation. It's still in terms of f. It depends on the original function still. This one doesn't. This is just straight up the new equation after the transformation. What do we get? We get the line y equals 2x minus 6 after messing around with this in the ways we've set out. Okay, just to illustrate the difference between those two one more time, right? Here is our original function, okay? In blue, I've got f of x equals x plus 4. That's the equation f of x. That's what it looks like if we graph that line. It's the line where y is equal to the x value plus 4, okay? Now, for Desmos here, I've defined f of x. So what I could do is I could say, all right, show me g of x, and I could explain to it that g of x is like f of x, except instead of being f of x, I've replaced x with 2 times x minus 5, right? And that does work, but again, it still depends on that f. What I'm going to add in here, look at that. Look at that third one. This is what we got by actually doing those transformations, right? The equation g of x equals 2x minus 6. Notice that does not need to refer back to f of x. It's just saying if you do those transformations to the equation of f of x, you'll end up with that equation. So we can just graph that equation. G of x equals 2x minus 6. So notice what happens here. This works, right? This is because Desmos knows what f of x is. If I take away f of x, it now has no idea what g of x means, right? Because it was depending on that definition of f of x. It was saying g of x is like f of x changed around in those ways. But what we've come up with is just the straight up equation for g of x by actually performing those transformations to the equation of f of x and seeing what the resulting equation is. So that's the difference between those two ideas, right? One depends on f of x. It's like f of x, but changed in these ways. The one we have here doesn't depend on f of x anymore, right? We used f of x to get it, but now that's just the equation of this line after those transformations have happened. All right, now, transformations done to y are being applied to the output of the equation, right? To the y values, the f of x, right? Y is just f of x, the whole function. So in other words, to the entire equation, because it's the whole equation that gives us that output y, right? We have y is equal to stuff, or f of x is equal to stuff, and all that stuff in that equation is what's calculating our y for us when we put inputs through the function. So, for example, if we wanted to vertically stretch f of x equals x plus 4, we'll use the same function as we were just looking at, by a factor of 3, so that our a is 3, right? We're going to multiply every y value by 3, and then move it 2 units down, so our k is negative 2. We're going to shift every y value down by 2, subtract 2 from each y value. Then the above function, f of x equals x plus 4, is going to become, well, y equals 3 times f of x minus 2. Notice, what are we doing? We're multiplying the y values by 3. Y just used to equal f of x. Now it equals 3 times f of x. And then we're also shifting them 2 down. So we subtract 2, right? This is just our function notation. It's just a and k in their usual spots, right? A and k. But it's showing us what we're actually doing. Y was just equal to the original f of x. On this transformed function, whatever it is, those f of x's that were equal to y have been multiplied by 3 and then had 2 subtracted. Now, We know, though, that f of x, our original function, is just x plus 4, right? So if we're taking the original function, x plus 4, and we're multiplying its outputs by 3, then we can put in that x plus 4 there, and then we're subtracting 2 from them, right? So we just have 3 times f of x minus 2, but f of x is x plus 4. So now, this is the equation of the transformed function. We can just simplify it a bit more because I can multiply the 3 in, so 3x plus 12 minus 2 to give me y equals 3x plus 10. And again, look, see the difference here, right? This is the equation of the transformed function in function notation in terms of f of x. It still depends on f of x, right? It's saying the transformed equation is like f of x, but different in these ways. This one doesn't have to say that. It says, okay, whatever line you make after messing around with f of x this way, this is what your line you will have. You will have y equals 3x plus 10. That's your new line. That's your new graph, right? That is a linear equation that we could graph and come up with without even ever having to know what f of x was. We got it from f of x, but now we figured out its equation. That stands alone, okay? So you can probably see here, hopefully, that it's very helpful to first represent the transformations in function notation. Because what this lets you do, again, that function notation literally acts like instructions on what to do to the original equation to get the transformed equations. Because it just lets you easily see what you're going to be replacing x with in the original equation. That's kind of part one. And then what you need to do to the entire equation, right? So when we look at something in function notation, once we understand how to read this, we can see how it's really just step-by-step instructions on how to get the transformed equation, right? We used to have y equals f of x. That was our original equation, okay? And now we have y equals a times f of bx minus h plus k. So what did we do? Well, instead of an x, we have a b times an x minus h. So this part shows us what we're going to replace x with in the original equation, right? We used to input x's, now we're going to input b times x minus h's, right? And then what do we do to that? We take f of b times x minus h, we multiply it by a. And then what do? We add k to that, right? So I like to break these down into those two parts, actually. Not always. I mean, it's not always mandatory to do it. It's never mandatory to do it. It's not always that much easier even to do it, but especially with ones where you have like an A, a B, an H, and a K, you've got a lot of stuff going on, right? I often like to break it down into kind of two parts, right? We know that ultimately what we need to find is y equals A times f of bx minus h plus k. So I like to first just figure out what that f of bx minus h part is going to be by just taking my original function and replace x with b times x minus h, right? And there we go. What will we have found? We'll have found this part, right? Just by replacing x in the original function with b times x minus h. And then, see the instructions part? It tells us what to do with that f of bx minus h. It says multiply it by a and add k, right? So multiply whatever the result of substituting b times x minus h is in, right? Multiply the result of that by a and then add k, and you will have found the transformed function. You might have to do some simplification, but you will have found the equation of the transformed function. So let's try this out. Let's try it out by combining all of the transformations we just looked at for f of x equals x plus 4. So now we're going to do all of those things we talked about, not just the horizontal and just the vertical. We're going to do all of it. So we're going to make a equals 3, b was 2, h was 5, and k was negative 2. What would that look like? Well, in function notation, right, y equals a times f of b times x minus h. And then outside of those function brackets, minus 2, plus k, right? Plus k. So look at the instructions. Do you see what I mean? It's saying first, if you can figure out what f of 2x minus 5 is, you'll be on your way. So that's what I kind of do first here. Let's replace x with 2 times x minus 5 in the original equation. Our original equation was f of x equals x plus 4. So what is f of 2x minus 5? It's 2x minus 5 plus 4, right? X has just been replaced with 2 times x minus 5. We've replaced x with b x minus h, okay? And there we go. We've now found this part. That's that part of the transformed equation. And then it says, okay, so now take that, multiply it by 3, and subtract 2. It's up to you. You could simplify this a little bit first. I might actually do that, right? 2x minus 10 plus 4, and then combine like terms, okay? But either way, now that we know f of 2x minus 5, this says multiply it by 3. So look what I'm doing, multiplying it by 3, our a value. And then from that, subtract 2. Subtract 2, right? And if you simplify this all out, if you multiply it all out, you can check my work, you end up with the equation of the transformed function, y equals 6x minus 20. Again, this one is in terms of f. It still depends on f, right? This one is just, that's the equation of the line. You take the original line we started with, you do all this stuff up to it, you're going to end up with a new line, right? You're horizontally stretching it, vertically stretching it, and then horizontally and vertically translating it. That's going to give you a new line. And that new line will just be the line y equals 6x minus 20. That will be the equation of the new line. Okay. Time just to really drive the point home, right? There is y equals x plus 4, okay? If we mess around with it, right, if we stretch it and translate it, we're obviously going to move that line around. And it ends up looking like this red one. Now that is defined, you can see on the left there, based on what f was, right? But that is a line. Every line has an equation. We found that that line's equation is 6x minus 20, right? If you imagine taking that blue line, stretching it, translating it, you can see how you could eventually bend it to look like that red line there, right? And that red line, again, every line has an equation. So once again, if I take away f of x, it's not going to know what I mean for g of x there in terms of f of x, because it's based on f of x. So if I take that out of here, boop, it gives me an error. It says, I don't know what f of x is. How am I supposed to show you g of x when it depends on f of x? Now we've come up with an equation just for that line on its own. So that's the difference between our function notation equation and just the actual straight up equation for the transformed graph. With that under our belt, let's try some of these out. Let's see if we can apply that process, right? Just got to figure out what to replace x with, and then what are we multiplying to the equation and or adding to the whole equation. So the equation for the function y equals f of x is y equals x squared plus 3x. Determine simplified equations for the following transformed functions. First up, y equals f of 2x. So this is a horizontal stretch by a factor of 1/2. We can see that b is 2, right? It's instructions. It's saying if this is f of x, we want to find f of 2x. So our b is 2. This literally means replace x with 2x to get the transformed equation. So let's do that. We had y equals x squared. Wherever I see an x, I'm going to replace it with a 2x. Y equals, oh, pencil's not working. There we go. Y equals 2x squared plus 3x, so plus 3 times 2x. Okay, all I've done there, replaced x with 2x, right? There's no a there, there's no k, there's no h. So all I'm doing is horizontally stretching it, and that just means I need to replace x with bx, 2x in this case. So simplifying that out, 2x squared, well, 2x times 2x, 2 times 2 is 4, x times x is x squared, plus 3 times 2x, well, 3 times 2 is 6x. So y equals 4x squared plus 6x. There we go. That's the transformed equation, right? If I were to horizontally stretch this by a factor of 1/2, it would end up looking like the parabola y equals 4x squared plus 6. Cool, right? Okie doke. What's this saying to do? Can you see the instructions here, right? We want to go from the original equation, y equals f of x, to this transformed equation, y equals negative f of x. So this is still f of x. It's saying the transformed one is just negative f of x. So those are instructions, right? We've just got an a of -1, right? We just have to take the original f of x and multiply it by -1. So we're going to multiply f of x, all the y values, by -1. Okay, so here we go. Y used to equal x squared plus 3x. We're going to multiply that all by -1. Right? So just basically distributing that -1 into the brackets. -1 times x squared is -x squared. -1 times 3x is -3x. And so if we reflected this in the y-axis, in the x-axis, it would end up just looking like the parabola y equals -x squared minus 3x, right? This is the equation of the parabola that we get if we reflect this one in the y-axis. Alrighty, last one here, though it's got multiple parts. The graph of y equals f of x is, okay, here we go, stretched vertically about the x-axis by a factor of 2. So vertical stretch, factor of 2, that means a is 2. Ooh, reflected in the x-axis. So we spoke too soon. Is a 2? Well, the absolute value of a is 2, but a is actually -2, right? If we reflect it across the x-axis, we need to be multiplying the y's by not just 2, -2 to get that reflection. Okay, so what we just established in part A there, right, is that in general, for any function f of x, if we wanted to transform it in these ways here, right, this is what we would end up doing to the equation of f of x, right? We would alter it in these ways. Now, f of x is just still any equation, right? There's not a specific f of x. That's what we're getting into in B here now, right? In B, it's saying, what if the actual specific equation, y or f of x equals x plus 7 were to undergo these same transformations? And that's why this is so helpful to write this notation first before you try to do these kinds of questions, because now this really acts like instructions, right? It's saying for whatever your f of x is, if you want to transform it in these ways, what you're going to end up doing is replace x with this stuff, then whatever that gives you, multiply it by -2 and add 3, right? So let's try that here. Now we actually have an original f of x that we're starting from, not just some general, f of x could be anything, but what if f of x were x plus 7 and we transformed it in these ways? What would be the equation of the new line that we would end up with after messing with that graph in those ways? Okay, so let's see. We have that, originally f of x is x plus 7. Now, again, I kind of like to break that up into these two parts, not mandatory by any stretch, especially for more simple ones, but when things get more complicated, there's kind of two things we got to do, right? We have to replace x with this stuff. Then, part 2, we've got to multiply whatever that is by -2 and add 3. Possible to do it all at once, but I like to just first do, first replace x with bx minus h. And then I can think about, all right, and then whatever that gives me, I'll multiply it by -2 and I'll add 3. Because we can see here, we really do, if we want to write this, first things first, well, maybe not first things first, but one of the things we have to do is find f of 2 times x minus 6, okay? So if f of x is x plus 7, what is f of 2 times x minus 6? Well, I mean, if f of x is x plus 7, what's f of 1? What would you do? You would replace x with 1, right? It's no different here. We want to find f of 2 times x minus 6. So what are we going to do? We're going to replace x with 2 times x minus 6. So I have x plus 7. Instead of that x, though, I'm going to replace it with a 2 times x minus 6, right? All I've done there, x, x. And I still have to do the plus 7. So plus 7, right? Okay. And so now, I mean, we could technically go ahead and multiply by -2 and add 3. Often it's nice to just simplify this part first, though, just so we don't have to worry about so much to deal with once we do those other steps. So I'll say f of 2x minus 6 is just going to be equal to, let's distribute that 2. So 2x, 2 times -6 is -12 plus 7. So what we've just found is f of 2 times x minus 6. And 2x, -12 plus 7 is going to be -5, right? So f of 2x minus 6 is just 2x minus 5. And we can refer back to here. These are our instructions. We knew we had to find f of 2x minus 6. We just did. It's 2x minus 5. And we can refer back to here, and it says, okay, well now, right, now multiply it by negative 2, add 3, right? We just found this part. So, okay, we can multiply by a and add our k. We kind of do the inner stuff and then the outer stuff, the x stuff and then the y stuff, so to speak, right? So now we know that y is equal to a times f of 2x minus 6 plus 3. We found that f of 2x minus 6 is 2x minus 5. So we're going to multiply that, right? What does it say to do? Take that, multiply it by negative 2. So negative 2 times 2x minus 5, and then plus 3. Plus 3. So the equation of the transformed function, I mean, that's technically it, but we should probably simplify this a bit, right? So negative 2 times 2x, negative 4x. Negative 2 times negative 5 is positive 10. And negative, whoops, sorry, no, that 3 is just being added. I forgot that the brackets weren't around the 3. So plus 3. And then y equals negative 4x plus 13. And there we go. Y equals negative 4x plus 13. That is the equation of the line that we would get if we took the line y equals x plus 7, stretched it vertically by a factor of 2, horizontally by a factor of 0.5, reflected it in the x-axis, then translated it 6 right and 3 up. All right, so same idea here now. It's saying, what if you did the same stuff, but f of x was x squared plus 2x? Still the same idea, right? We found in general how to transform any function, and now it's just saying, all right, well, do it to this function. So our f of x now is x squared plus 2x. Again, I like to kind of split it up into those two steps. You definitely don't have to always, but especially with ones, you know, where we're squaring stuff, it can get a little hard to keep track of. So I like to first just, you know, find f of bx minus h, which is exactly what it sounds like. It's f of x, but you replace x with bx minus h. Okay? So first find this, so that then we can multiply it by negative 2 and add 3. So what is f of 2 times x minus 6? If this is our f of x, well, wherever I see an x, I'm going to replace it with 2 times x minus 6. So I see an x squared there, so I'm going to put in a 2x minus 6, and that x was getting squared, so don't forget to square it. Okay, plus 2 times x, but I'm replacing x with 2 times x minus 6. So let's just keep simplifying here. Now, again, I might first just distribute this 2 in before I square that binomial. Might just be a little bit easier to think about. So I'll do 2x minus 12, and then that's going to be squared, plus, you can do the 2 times 2 is 4, x minus 6, just kind of working on breaking this down and simplifying it. 2x minus 12, okay, let's expand that out. Remember, 2x minus 12 squared means 2x minus 12 times 2x minus 12. And while I'm here, I might as well now distribute that 4 in. So 4 times x is 4x. 4 times negative 6 is negative 24. And then we're getting there. We just got to keep multiplying this out. Okay, so I would do, again, both of these terms need to get multiplied by both of these terms. So 2x times 2x, that's 4x squared. 2x times negative 12, that's negative 24x. Negative 12 times 2x, negative 24x. Negative 12 times negative 12 is positive 144. And then we've got our plus 4x minus 24. And we're just about there. Now we know that f of 2 times x minus 6. All that's left to do is collect like terms before we go ahead and deal with the a and the k transformations. So this is 4x squared. Negative 24x minus 24x is going to be negative 48x. Negative 48x plus 4x is negative 44x. Okay, so I've combined all my like terms. And then 144, positive 144 minus 24, that's positive 120. All right, So that is f of 2x minus 6. Okay, so we found this part. Now what do we got to do with it? You got it. Multiply that by -2 and add 3. So step 2, okay, essentially now we find -2 f of, well, af, I'll just keep it general up here, find af of bx minus h plus k, right? But we'll make it specific to ours when it's actually time to do it. So the general, the equation of the transformed function is going to be y equals a times this, right? A times f of 2x minus 6, according to our, instructions that were given by our function notation. So I need to do -2 times what we just found, right? What we just found, f of 2x minus 6, which happened to be 4x squared minus 44x plus 120. And then to that, what do? We add 3. So plus 3. All right. So now we get y equals, let's distribute this -2 in to kind of simplify. So -2 times 4x squared is -8x squared. -2 times -44x is positive 88x. And -2 times positive 120 is -240. And then we've got this plus 3 that's along for the ride. And all it's left to do is combine like terms, so nothing to combine with the x squared term, nor the x term. However, -240 plus 3, we can combine those into -237. And there we go. That's the equation of the transformed function, right? Not in terms of the original. That is just straight up the equation of the parabola that we would get if we did all of those things to this function. Cool, right? All right, so let's just take a look at this really quick. That's the equation we just did, right? In red there, we've got f of x equals x squared plus 2. I'll just move it so you can see, okay? F of x equals x squared plus 2x. That was our original function, the one we started with. And now in purple there, this one, that is what you get if you graph y equals -8x squared plus 88x minus 237, which was the equation we came up with for the transformed function. Now in blue, what I've got, notice that's just g of x is equal to, and I've got the af b of x minus h plus k going on there. And I can adjust the a, b, h, and k. Again, I would suggest you check your work on your graphing calculator because that's what you'll have access to on the diploma. The reason I'm using Desmos is it lets me do these nice kind of visuals to show it when I'm teaching this stuff, okay? But let's just do that. Let's watch the transformations occur to f of x by adjusting the a, b, h, and k that we have in, and let's see if it matches up with the equation of this parabola, which is what we wrote as the transformed parabola's equation. Okay, so here we go. I'm going to make a -2, because that's what our a was. So as we would expect, it's reflected it in the x-axis. It's vertically stretched it by a factor of 2. Our b value was 2. So it got narrower. We would expect that because every x gets multiplied by 1 over 2. And then h was 6 because we translated it 6 units to the right. Ooh, this is looking kind of promising. And then k was 3. So we translated it 3 units up. So did you see that all happen? Right? Look where it ended up. It ended up in the exact spot of that transformed equation's parabola, right? Because that's what it is. It's just saying if you were to transform x squared plus 2x in those ways, you'd end up making the parabola y equals -8x squared plus 88x minus 237, right? And sure enough, that's exactly what we saw happen there as we went through those transformations. Okay, one more time because it's very satisfying. Let's just watch it again. A -2, B +2, H +6, and then K +3. Right? Pretty neat. So go ahead. We are done the examples there. That's it for the notes and the worked examples. Sorry, my dog's barking in the background. But go ahead. This is a good one to try now while it's fresh in your brain, right? Writing the transformed equation based on the transformations that are occurring. Again, my advice with these, write it in the function notation first, right? Find your a, b, h, and k, and then write it out like this, because that then acts like instructions on what to do to the original equation f of x in order to get the transformed equation, right? Replace x with b times x minus h, then whatever that gives you, multiply it by a and add k. All right, and that's it for lesson 5, and therefore that is it for unit 1. So you are now able to do the topic 2 quiz for unit 1, and you are now able to set up a time to do your unit 1 test. Okay, make sure you're reaching out with questions, right? Joining the help meets or booking a time with me through You Can Book Me. I'm happy to help, right? But yeah, there's unit 1. 1 down, 4 to go. Hard to believe already.